In today's session, one of the flip-flop which is SR. So in last class we learned about your latches of NOR as well as your NAND. So those latches outputs depends only on your present input logical levels, whereas in flip-flops we have a control element called as trigger signal. That trigger signal can enable your sequential circuit output. So since if there is no control input in your latches, outputs only depends on your signal levels of your input. So when it depends on your signal level, so if it doesn't have any control signals, there is an uncertainty at your output of your latches. So simply it will store based on your inputs. So hence in order to control that operation and to avoid that instability and to have your more stable states at your output of your flip-flops, so we were going to use the clock signal. What is a clock signal? Actually, a clock signal is a periodic pulse signal which can maintain the low level as well as a high level voltages on a regular time period. So now basically we are going to use a clock signal is a square wave signal which is generated by your digital oscillators and which can oscillate in between the two voltage levels, a high voltage level as well as a low voltage level. So since I'm going to take a symmetrical square wave which consists of the high time period, high voltage level time period is equal to the low voltage time period. Hence it is known as your 50% duty cycle. So is defined that equal time intervals on your high voltage time period as well as your on your low voltage time period. So one cycle of your signal is known to be a complete. So the time period which is taken for a cycle to complete one complete cycle of your clock signal is known as your one clock cycle, which consists of a positive or high voltage level time period in addition with your low voltage time period. So based on here, a clock signal is having two levels of differences. So in its voltage levels, a high voltage level as well as low voltage level, and also we would also have one more parameter which is a raising edge of your clock as well as the falling edge of the clock. So raising edge of the clock is defined as when your clock is moving from low level to the high level, and falling edge of the clock is defined as when a clock is moving, the instant where the clock is moving from your high level to the low level is known as your falling edge of your clock. So based on whether your clock is at high level of time period or low level of your time period, or your whether your clock is at a raising edge of your clock or falling edge of your clock, if it changes their output of your sequential circuit based on these levels as well as your changes in your edge triggerings, so then they are classified into two categories as level triggering and edge triggering. In level triggering, the circuit is triggered or your sequential circuit will generate the output so only on your high levels or your low levels. So if your sequential circuit output changes on your high level, then it is known to be the positive level triggering. If your sequential circuit output changes on your low level, then it is known to be the negative level triggering. Next, based on your raising edge or your falling edge of your clock, so your edge triggering is classified again into two categories as negative edge triggering and positive edge triggering. If the state of your circuit or your sequential circuit output is generated on your positive edge triggering, so when your clock is moving from low to high state, then it is known to be the positive edge trigger. So if your output of your sequential circuit will change only or your inputs can have a chance to change its next state of your sequential circuit only on your clock when it is moving from high level to the low level, then it is known to be the negative edge triggered flip-flop. So these are your basic triggering methodologies which I am going to use on your clock of your flip-flop. So now based on this, so your flip-flops are classified as positive level triggered flip-flops, negative level triggered flip-flop, or your positive edge triggered flip-flop or your negative edge triggered flip-flop. And we have basic symbols in order to indicate your that type of triggering. So now that type of triggering is here. I will note it down that type of your triggering as here positive level, so which is indicated the clock symbol, so with a sleeping line, so then it is your positive level triggered flip-flop. For example, if it is a SR flip-flop which is having two inputs, so in here Q and Q bar are my outputs of your flip-flop. So this is your positive level, and negative level symbolized as your clock is with a bubble. So this can give you the negative level triggering logical symbol of your block diagram of your flip-flop. Next, positive edge triggering is indicated with a arrow with a sleeping line, and the arrow inside that block is indicated with your negative edge triggered symbol, and a positive edge triggered, and negative edge is indicated a arrow inside the block, as well as along with this sleeping line we also have your bubble. So this indicates the negative edge triggered flip-flop symbol. So positive level, negative level, this is your positive level flip-flop symbol at your clock, and this is a negative level symbol of your flip-flop, and this is your positive edge triggered flip-flop symbol, and this is your negative edge clocked flip-flop. So like this, so we have four types of triggering. Now, so let me move to your types of, based on your clock signal, based on your external inputs, so your output will change in your sequential circuit. Based on this, we have basically those sequential circuits are constructed using your flip-flops. Now, we have basically four types of flip-flops, which are SR, D, JK and T. So basically these D, JK, T flip-flops are the three different modifications which we have done on your SR flip-flop. So first let me learn about the basic flip-flop, which is SR. So here we mentioned SR means set, S means set input, R is defined as your reset input. So why we name this as a set input is set can, if you are enabling your set input is logic 1, your flip-flop is loaded with your logic 1 state. So if your reset input is 1 and set input is 0, if your flip-flop is loaded with your logical 0. Hence, so set input 1, so which can set your flip-flop or loads a logic 1. If your reset input is 1, it will load your flip-flop with your, or stores your flip-flop with your logical 0. Hence, these are named as your set or reset flip-flop, and these flip-flops are constructed using NAND and NOR gates. So NAND and NOR are your universal gates, as we already learned that. So now, so this is your block diagram which consists your two inputs only. So as flip-flop is having a number of inputs, but in an SR flip-flop only we have two inputs which are SR, and two outputs. In any flip-flop we have only two outputs which are complemented output Q bar, and uncomplemented output is Q. Now, so let me draw the logical diagram of yours flip-flop, SR flip-flop using the NAND gates. So now here I will mention here the numbers of your NAND gates. So used to construct your SR flip-flop is four number of NAND gates. So now 1, 2 are used in order to obtain the synchronization with your clock signal. So in 3, 4 are your NAND gates which is acting like a active low input latch, so which is a NAND latch. Now until unless the clock is 1, so no input will change the output of your SR flip-flop. If clock is 0, so then your S input might be a don't care, or your R input is a don't care. So don't care means whether it is a 0 or 1. So because of one of the input of your NAND gate is 0, and this first NAND gate output will give you logic 1, second NAND gate output is also giving the output which is equal to logic 1. So on your active low input SR latch, if I have 1, 1 on your SR latch, the previous state is continued as your next state of your output. So Q is 0, so next state is also equal to 0. If Q is 1, next state is also equal to 1. So which defines the no change state. So when your clock is 0, so or we will directly define. So if clock is not enabled, so this defines your state of your no change state, or it is in off state. So hence here, so when clock is 0, it is defined as your off state. When clock is 1, now it will allow your sequential circuit to change its output by the external inputs. So now when clock is 1, so your outputs of your these two NAND gates of 1 and 2 are dependent on your S and R inputs. So if S is 0, R is 0, again we are getting the same combination, like first gate output will be 1 and second gate NAND gate output will be equal to logic 1. So present state is 0 or 1. So next state is a no change state. So hence present state, if it is 0, next state is 0. If present state is 1, next state is also equal to 1. So since my active low input SR latch inputs are 1 1, so for such input of 1 1, we obtain your no change state on your SR flip-flop. Next, so let me treat your S input is 0 and R input is 1 along with clock equal to 1. So since S is 0, so if any input of 0 on your NAND gate can give you the output of your logic 1. If all inputs are 1 on your second NAND gate will give you the output of 0. So immediately here your present state is 0 1 0 or 1. So your complementary state, if it is 0 or 1 on your present state, so your complement state is 1 or 0. Immediately this fourth NAND gate output, now it will be transferred to a logical 1. So since my one of the input of your fourth NAND gate is 0 and that one is transferred as your second input of your third NAND gate, so hence your present state is 0 or 1, next state is equal to a logical 0. Since our input is 1, we obtained a state called reset state here. So next we'll take your next case, which is your S input is 1 and reset input is 0. So along with clock equal to 1. So here when your reset input is 0, so output of your NAND gate is 1, whereas here when both inputs of your S and clock are 1 on your first NAND gate, so since that the first NAND gate output will give you the 0. So if you are giving a 0 input on your NAND latch, your present state is 0 or 1, next state is always equal to logic 1, and this 1 is transferred as your second input, hence your next state of complemented state is 0. So since S input is 1, set input is 1, reset input is 0, your flip-flop is set to logic 1. Now, so when I am applying the last input condition, which is the last case, which is S input is 1 and reset input is 1 along with clock is 1. So both first and second NAND gates will give you the 0 outputs. So hence here both are 1s. So set input is 1 and clock is 1. Here reset input is 1, clock is 1. So hence second NAND gate will now give you the output 0. First NAND gate is also giving the output. So Q is 0 or 1. So your output of this will be 1. So Q bar is 1 or 0. Your output of this so gives you the logical 1 state. So now in your Boolean algebra, so if A is 0, A bar must be equal to 1. So this is called as complementation. If A equal to 1, so A bar must be equal to 0. But here if Qn is 0, Qn bar must be 1. That is a natural complementation law. So now in this case, which is your last case, S is 1, R is 1. So you are getting Q is 0, next state is Q is 1, as well as Q and bar is also equal to 1. So both are logical ones. So hence only that case of S equal to R equal to 1 is treated as your invalid state of your flip-flop. So here I will mention that states. So first 0 0 SR inputs, which is no change state, hence present state, next state is continued with your present state. Next 0 1 on my reset input is 1, hence present state is 0 or 1, next state is a 0. If your set input is 1, so present state is 0 or 1, next state is 1. So reset input is 0, set input is 1, present state is 0 or 1, next state is 1. So if my last case is SR inputs are 1 1, present state is your invalid state, present state is 1, also invalid state. So like this, so we are going to define the working of your SR flip-flop. Next, from this SR flip-flop, we have to draw the characteristic equation. Characteristic equation, now it depends on your present input as well as on your present state of your circuit. Now, your characteristic equation is derived from its state table of your SR flip-flop. Now, if I am going to write your standard SOP expression of your Qn plus 1 in terms of your SR Qn as, so here wherever the min term functional value is 1, that min term we have to consider inside the parenthesis. So sigma m of 1 comma 4 comma 5 is your min terms, and it also have your don't case which are 6 comma 7. So now upon mapping your function using the three variable s, r, q, n are my input variables, and mapping your function, then grouping the min terms, so we can form one 4 square adjacency, another one which is a 2 square adjacency. That 4 square adjacency will give you the common variable which is s. Row wise s variable is 1, so hence it is s. For pair formation, so row wise, so s variable is different, only the column wise r and q and r common, so they are same for these two minterms, hence so 0 1 is on your r is 0 since r bar, and q n is value is 1, so the product term we mentioned r bar into qn. So characteristic equation of your SR flip-flop is equal to qn plus 1 is equal to s plus r bar into qn. So from this characteristic equation, let me derive here the excitation table of your SR flip-flop. Now, in the SR flip-flop, excitation table is a table which can give you the state transition from input present state to the next state, and in order to obtain that state transition on your present state to next state, what are the excitation inputs required, or the external inputs required. So now in your state table, so here if you have taken this, so 0 0 is arrived two times, so s is 0, r is 0 in the second case, so the 0 0 arrived in your 0 on your s input as well as your r input is equal to 1. So just by observing these two cases, s is always equal to 0, r is equal to a don't care. Hence 0 to 0 transition, s always must be 0 and r might be a 0 or might be a 1. You would obtain your state transfer from your 0 to next state as a 0. The same manner 0 to 1. So now by just saying that in your state table, 0 to 1 is obtained on your set when your set input is 1, reset input is 0. Hence set input is 1, reset input is 0. Next 1 to 0. So 1 to 0 transition, by just looking at excitation inputs, s must be 0 and r must be equal to 1. The last one is 1 1 transition. So that 1 1 transition is occurred twice on your SR state table. So these two are your state transition 1 to 1. So in this 1 to 1 transition, S input must be 0, R input is 0 is the first case. Second case is S input is 1, R input is a 0. Hence, R value is always, from this observing your two cases, R is 0, S must be a don't care. So hence, 1 to 1 transition is don't care and 0. So these excitation tables are very useful while you are designing your registers or your counter. So hence, for every flip-flop, you have to derive the characteristic equation from your state table along with that excitation table from your state table of your flip-flops. So this is of your SR flip-flop. So next, in the next class, let me learn about your clock D flip-flop.